Hello student, welcome to the tutorial session. Today's topic is combinational logic circuit. So first we have to understand that what is combinational logic circuit. So combinational logic circuit is compromises of the basic logic gates whose output of any point of time only depend upon the current input, not on the previous input. Again I am explaining. So to design a circuit we require this basic logic gates. Not only basic logic gates, universal gate also sometime needed to make a circuit. So when you giving the input to the particular circuit, the output of the particular circuit only depends upon the input what you are currently giving it to it. Okay, whatever previously you are giving the output, that will not determine the current output of a particular circuit. This is actually called the block diagram. For each and every combinational circuits, you have to mention the block diagram. Okay, what this block diagram explains? This square box represents that it is a combinational logic circuits, and here these arrows represent that there is a n number of input we can give to the combinational circuit, and depending upon the n number of inputs we can get m number of outputs through this circuit. Okay, so there are different characteristics are there through which we can identify a circuit is a combinational circuit or a sequential circuit. So what are those characteristics? So first one, it says the output of the combinational circuit at any instance of time depends only on the level present at the input terminal. So what output you will get right now, it is only depends upon that what input you have given to the particular circuit right now. Okay, next feature is that the combinational circuit does not use any memory. The previous state of an input does not have any effect on the present state of a circuit. So it does not consist any memory space. So if does not contain any memory space, so the previous output it will not able to hold. If the previous output it will not able to hold, then it will not affect the current output. It is saying that only the input whatever you are giving right now, it will affect the current output, not the previous input. Okay, another thing, the combinational circuit can take n number of inputs and can give you the m number of outputs. Okay, next is we have to understand that how many type of combinational circuits are there. Okay, depending upon the work it will perform, we can classify the combinational logic circuit in three ways. Okay, so first one, the circuit which will perform the arithmetical function. Second one, the circuit which will help to data transmission, and third one, will circuit help to converts. Okay, so under the arithmetic function, what circuits are present? That is adder and subtractor. Okay, adder will do what? Adder will add the binary digits, and subtractor will be subtract two or more binary digits. Multiplex and the data transmission from one place to in other place, if you transmit the data, so we need the multiplexer and demultiplexer, and decoder and encoder also required. When we actually transmit the data in a network, it will be encoded, and when it will reach to the destination, it must be decoded. And the code converter is not included in your syllabus. This part is not included, only these two we will learn. Okay, so adder, we have to find out the adder. There are two type of adder. One is half adder and another one is full adder. The half adder will add only a single bit binary information, and full adder will add the multiple bit of information. Okay, I am proceeding and I will explain the half adder in details. So what is the definition of a half adder? Half adder is a combinational logic circuit with two inputs and two outputs. Only you will pass two inputs and you will get the two outputs. Okay. Half adder circuit is designed to add two single bit binary information. Remember that half adder only add two single bit, that 0 plus 1 or 1 plus 0, like that. So suppose that A is the input and B is the another input. So we will get the two output. One is called sum, another is called carry. Because you know, if you recall it, the binary addition rule, that 1 plus 1 is what? The answer is 1 0. Okay, so 0 we are writing in the sum part and carry 1 is there. So that's why in adder we will get two output. One is the sum output, another one is the carry. This one is the block diagram. Just look it closely. You are passing the input A to the half adder and one single input in a B. So what we are getting? We are getting sum as a output and carry is a another output. Okay. Now I explain this phenomenon with the help of truth table. See, if we add 0 plus 0, then what will be the output? 0 plus 0 is 0. There is no carry. 0 plus 1. And I apply the binary rule. 0 plus 1 is also, sum is 1. There is no carry. If you try to add 1 with 0, the answer is same as sum. The sum is 1 and there is no carry. But if you try to add 1 plus 1, 1 plus 1, it means what? 2, 2 in decimal. And if you convert it into binary, so what will be the output? 1, 0. So 1, 0 is we will write in the sum part and 1 we will write in the carry part. So that's why here we need two output channels. Okay, one for the sum part and another for the carry one. Next, this is actually the circuit diagram. Okay, so the sum expression is how we are designing. We are passing the X input and Y input through the XOR gate. So this one is the XOR gate expression. X bar Y plus X Y bar. In the previous logic gate, I have explained what is the functionality of the XOR gate, how we can derive it. So if you just look at this part of the table, you will see that this is exactly the truth table of XOR gate. So that's why some part is denoted by this XOR gate. And if you look at the carry expression, this is exactly same as the AND gate truth table. So that's why A and B, this part, C part, that is X and Y, it is written. Okay, this will denoted by the AND gate. Now come to the full adder part. So in case of full adder, what we are doing? Full adder actually helps to remove the drawback of the half adder, because using half adder we can only add a single bit binary number. But in case of full adder, using the full adder we can add two bit information. Okay, say A and B is there, because here why, ma'am, you can ask that why C is there? C is for Y, because if you try to add multiple, just was 4-bit binary information is there with you, 1 1 1 1 0 1 1. So 1 1 plus 1 is what? 0 and carry 1. So carry we have to propagate with the next bit. So how we can add this carry? This C in is represent the carry from the previous bit. Okay, the C represent the carry from the previous bit. And here we are adding the digits and we are getting the sum and getting the carry part. Okay, now with the help of truth table, I will explain this topic. Okay, so 0 plus 0 is what? 0 plus 0, and C in means previously when you try to add the first bit number information, there is no carry is there. So 0 plus 0 plus 0, sum is also 0 and carry is also 0. So 0 plus 0, if carry is there, so what will happen? 0 plus 0 plus 1. So 1 is in the sum part, carry is 0. 0 plus 1 is 1. 1 plus 0, sum is 1, carry is 0. 0 plus 1, the answer is 1. But again we have from the previous carry is there. So 1 plus 1 is what? 0, and carry is there. So carry is 1. 1 plus 0 is 1. 1 plus 0 is 1. Again 1. So in the sum part there is a 1 and carry is 0. Next, 1 plus 0, the answer is 1. Again 1 plus 1 is 0 and carry is 1. 1 plus 1, 1 plus 1, sum is 0, carry is 1. So that's why carry written over here 1. And 1 plus 1, sum is 0, but 0 plus 1, answer is 1. And 1 plus 1, carry is 1. So carry I am writing over here. Now let's look at the circuit diagram. Okay. So circuit diagram explain that this is A, B and C. Both the inputs are passing through the XOR gate. And next AB and ABC in and BC in. These are actually the expressions for the carry part. Okay. Again it will come to the XOR gate and again we are getting this expression. Okay. So I am ending my lecture over here. Next time we will proceed through the subtractor one. Thank you.